Hello again. Today we're going to learn about a very special kind of expression that we're going to be seeing a whole lot of this semester. It's known as the polynomial. Now, before I can tell you what a polynomial is, I have to tell you what a power function is. Because polynomials are made out of many power functions. So first, let's learn what this is. A power function is any expression of the form a times x to the n. So a here is called a coefficient. X to the n is the main show. We've got a base and an exponent. That's the main part of the show, but it's also multiplied by a coefficient on the side. A coefficient is anything that's multiplied by the thing you care about. Okay, so this is a power function. Any number times x to the power of any number. Not any number. N has to be a whole number, like 0, 1, 2, 3, or so on, 4, 5, 6, and so on, right? So n can't be negative, it can't be a fraction, it can't be a weird decimal. A can be any of those things. A could be -5 or 12 or 1.5 or 3.14159 for all I care. But n has to be a nice whole number. Okay. So some examples. Let's see. Real bog standard example would be 3x to the 6th. Here, a is 3, n is 6. That's chill, that's cool. How about x squared? Well, clearly n is 2, but what's a? There's no coefficient here. Well, the trick is, anytime I don't have a coefficient written, that coefficient's essentially 1. X squared is the same as 1 times x squared, isn't it? So a here is a 1. We don't have to write that 1, but we can pretend it's there when we need it for to match this form. So how about this one? Here's another power function, 2x. Well, here clearly a is 2. That's the coefficient. It's the thing that's multiplied by the power of x. And that's right. X is the same as x to the first power, right? So n is 1. I don't have to write that first power all the time, but when I need it, it's there. It's like you know how words have silent letters sometimes? It's like an invisible number. It's exactly the opposite. It's there, but we don't write it. Here's one more. Here's one more power function. This one's going to be real goofy. 5. That's it. That's the whole power function. The coefficient is the 5. Well, what's going on here? There's nothing to the right of the 5. There's no, well, I know that any number to the 0 power is just 1, yeah? And I know that 5 is equal to 5 times 1, yeah? So I can shoehorn this into the form. I can say 5 times nothing at all. Well, it's really the same as 5 times 1, right? And 1 is x to the 0. So this is really a 5 times x to the 0. If I would never write it that way unless I wanted it to fit this form. But if I want to fit this into that mold, I will say that the power of x is 0. So those are power functions. That's all the variation power functions really get. Those are the different kinds of power functions. And now I can say a polynomial. This is the thing we were really after this whole time. It's a sum of power functions. So for example, I could take the 4 power functions from before and say 3x to the 6th plus, well, I don't need to write the 1, so I'll just write x squared plus 2x plus 5. This is a polynomial. A polynomial has a few important parts. I want to go over the anatomy of a polynomial, and we'll define 3 or 4 words. All right, first off, the biggest exponent out of all the power functions, in this case, that's the 6. This guy is called the degree. So the degree of the polynomial is whatever the biggest exponent is out of all of them. So each term is a power function. There are 4 terms here, but the one with the highest degree is this 3x to the 6. So 6 is the degree. If you have a term with no power of x, that's called the constant term. Constant term. So these are going to be the most important parts of the polynomial. The constant term is useful because if I plug in different values of x, like if I go from x equals 1 to x equals 2, this first term will go from 3 to 192. This next term will go from 1 to 4, and this term will go from 2 to 4. So all of these terms changed value, but whether x is 1 or 2 or a million, this is always worth 5. That's why it's called constant. Whatever term has the degree is known as the leading term, because usually we write it out in front. And whatever the coefficient is on the leading term, this is about the least creative name ever, it's known as the leading coefficient. So this polynomial has a leading coefficient of 3, a degree of 6, and a constant term of 5. Those are the 3 most important numbers in the polynomial. The terms in the middle tend not to matter as much for most applications. It tends to be the first one and the last one that have the most to do with how it's shaped. We'll see why later. We're not going to take a deep dive into polynomials right now. We're just going to be able to handle them as expressions. That means adding, subtracting, and multiplying them. We'll get to all that today. Anything past that, we'll do later. So let's do another example. If I had 5x cubed plus 4x squared plus 3x plus 2, here's a nice polynomial. Hey, notice how the degrees go 3, 2, 1, 0? Or up here they go 6, 2, 1, 0, or maybe they went like 7, 4, 3, 1. If they're in descending order, we call that standard form. Standard form is whenever a polynomial is written as a sum of terms in descending order. That's the nicest way to write a polynomial. It's really simple to read off each term in order. Okay, so our constant term is 2. Our degree is 3. And our leading coefficient, I'll write LC for short, is the 5. Because that's the 5 that's multiplied by the x to the third, and that third is the degree. So far, so good. Let's try a polynomial that's not in standard form. It's going to be all out of order. How about 4x minus x to the 7th plus 5x squared? This is full of tricks. This polynomial is full of trick questions. See if you can tell me what the degree is, what that means the leading coefficient is, and what that means the constant term is. Go ahead and pause the video for a second and see if you can work those out. Okay, so let's take a look. The highest power of any of these is the 7, so that's going to be the degree. Now the leading coefficient is whatever coefficient is on the leading term, and that's this one. It's the one with the degree. This isn't in standard form, so the leading term isn't out front where it belongs. So if I write negative x to the 7th, that's the same as a negative 1 times x to the 7th. So this negative 1 is our leading coefficient. Now here's the trickiest part. Did you get the constant term? None of these terms are without an x. So do you say it does not exist? Well, not quite. Just like I could say 2x is the same as 2x to the 1, or x squared is the same as 1 times x squared, I could say that this polynomial is the same as if I added 0 to it. That wouldn't change the value. So the constant term is 0. It still has a constant term, it just has a value of 0. So that's a dicey example. It'd be easier if we put it in standard form and wrote it as negative x to, that's not it, negative x to the 7th plus 5x squared plus 4x. That's a nicer way to look at it. Now you can see there's no constant term, so it must be 0. And the leading term is out front where it belongs, so the degree is 7. And the leading coefficient is -1, right here. In standard form, it's a lot easier to work with, but you won't always be given standard form, so have to be aware. All right. Let's talk about adding and subtracting polynomials together. The key here is just like with roots, we want to combine like terms. For example, 3x squared plus 5x squared is equal to 8x squared. But 3x squared plus 3x cubed is already simplified. There's nothing more I can do to that because x squared and x cubed are not the same power of x, so they're not like terms. Here, these are the same power of x, so they're like terms. I have 3 squares and 5 squares, so together I have 8 squares. But here I have 3 squares and 3 cubes. And that's not 6 of anything. I guess it's 6 shapes, but it's really apples and oranges. I don't have any symbolic way to smush those together. So we're not going to simplify that at all. So if I give you 2 polynomials, I might say the first one, let's say the first polynomial, let's call it A, is x cubed plus 3x plus 4. And the second one, B, let's say it's 3x squared minus 2x plus 1. And let's try to add and subtract those. So what do I get if I add these together? I have x cubed plus 3x plus 4, and I'm adding 3x squared minus 2x plus 1. Well, here we go. X cubed doesn't have a friend on the other side. It's the only term of its power, so it's just going to stay put. Now I could talk about the 3x next, but it'd be nice if my answer were in standard form without me having to put it there. So next I'm going to look at the power of 2. This 3x squared doesn't have any friends either. There's no second power in A. So 3x squared just stays itself. X cubed and 3x squared certainly aren't like terms. They're cubes and squares. They're apples and oranges. Now 3x and 2x, those are, oh, you know what? I like teal. Teal is good. 3x and 2x are like terms. If I have 3 x's and I take 2 x's away, I'm left with 1x. So instead of writing 1x, I'm just going to write x. And then 4 and 1 are like terms. They're both constant terms. 4 plus 1 is 5. So my final answer is x cubed plus 3x squared plus x plus 5. You see? Nice and simple. If I want to do a minus b, it's only a little bit more complicated. I have x cubed plus 3x squared plus 4 plus, whoops. I have made 2 mistakes. This is not a plus, and that was not squared. This should just be 3x. This should be a minus. This is 3x squared minus 2x plus 1. I could go term by term, and say the x cubed doesn't have any friends, the minus a 3x squared doesn't have any friends. Next, we have 3x minus a negative 2x. That gets us 5x. And finally, we have a 4 minus 1, and that gets us 3. So that's one way to solve the problem. Or you could say x cubed plus 3x plus 4. Or you could go right away, distribute the minus sign, and say it's like I'm adding a negative 3x squared, a positive 2x, and a negative 1. And now it's just like I'm adding polynomials. The x cubed doesn't have any friends, the negative 3x squared doesn't, 3x plus 2x is 5x, and 4 minus 1 is 3. Same answer, different method. Use whichever one you feel more comfortable with. That's how you add and subtract polynomials. Now let's talk about multiplying polynomials. I already showed you the distributive property, but I want to show you something a little different. Let's say I have x squared plus 3x plus 1, multiply that by another polynomial, 2x plus 7. Now I could say distribute the 2x plus 7 to each of these. So I could say I have x squared copies of 2x plus 7, 3x copies of 2x plus 7, and 1 copy of 2x plus 7. And then I distribute again, and I have 2x times x squared and 7 times x squared, 2x times 3x and 7 times 3x, 2x times 1 and 7 times 1. It's a lot of distribution. So this makes 2x times x squared. This is an x to the 1. That's x to the 1 plus 2, right? Product property. So this is 2x cubed. Does that make sense? 7x squared. 2x times 3x is 6x squared. 7 times 3x is 21 times x. 2x and 7. And now I just need to combine like terms. The 2x cubed is alone. 7 squares and 6 squares is 13 squares. 21 plus 2 is 23x, and here's a 7. That's the longest and generally the least fun way to multiply polynomials, but here's a shortcut. Here's a trick I like. See, it's like rows and columns. The x squared gets each of these, the 3x gets each of these, and the 1 gets each of these. So imagine I draw this shape. Here's x squared, 3x, and 1. They're each going to have a column. 2x and 7 are each going to have a row. And in the end, you see these 6 terms here? Each of these is going to get multiplied by each of these. So x squared will be multiplied by 2x and 7, 3x will be multiplied by 2x and 7, and 1 will be multiplied by 2x and 7. So I'll multiply each of these. Here's 2x cubed, here's 6x, here's 2x. Oh, 6x squared, my bad. 2x times 3x is 6x squared. Here's 7x squared, here's 21x, and here's 7. It doesn't always work out like this, but in this case, what's kind of cool is that the x squareds are here on this diagonal, and the x's are here on this diagonal. So when I combine like terms, I get 2x cubed, a 13x squared, 23x, and a 7. So that's a little bit of a faster way to arrive at the same conclusion as the box method. I already showed you if your polynomials are each, the word for them is binomials. Let me explain. Nomial or name in, I want to say Greek, it's analogous to what I've been calling a term. So if we have 2 terms, 2 bi, like a biplane has 2 sets of wings. So this is a binomial. Or this is 3 terms. I've got them underlined there. We'll call that a trinomial. Like a triangle has 3 sides, a trinomial has 3 terms. So that's a couple of words. And then, of course, poly. If you're polyamorous, you have a lot of boyfriends and girls, right? So polynomial just means many terms. So that's where these names come from. Man, I could have said a polymer is a plastic made of a bunch of different atoms chained together, but what did I go with? Inappropriate for class, Nathan. Too late now. It's in the video. I'm not re-recording this whole thing. Right, shortcut if you've got 2 binomials. That's what that whole tangent was supposed to express. Let's say I've got x squared plus 5 and, I don't know, x plus 2. These are both binomials. The shortcut for 2 binomials is FOIL. I think I showed you this last lesson. We go first, outside, inside, and last. And that guarantees, if I wrote this like the box method, x squared plus 5 for the rows, x or for the columns, x and 2 for the rows. The FOIL method guarantees that I get all these products. Let's see, this is first, this is last, this is inside, and this is outside. So FOIL is a quick acronym to make sure you get all 4 of these boxes without actually having to draw a box. Our answer is going to be first, x squared times x is 3. Oh boy, Nathan, that's not it. Sorry. Squared times x is x cubed, isn't it now? Outside, x squared times 2 is 2x squared. Inside, 5 times x is 5x. Wow, that's an easy one. And 5 times 2 is 10. That's last. So we ended up with a 3rd degree polynomial. Degrees are kind of how we classify polynomials. Since the highest power here is 3, we call this 3rd degree. Has another name, cubic, because power of 3 is like cubed. But I'll just call it 3rd degree for now. Kind of a fun fact, we'll come back to this later and it'll be very important. When I multiply 2 polynomials together, notice this was 2nd degree and this was 1st degree. 2 plus 1 is 3, so the answer is 3rd degree. Always works that way, every time. Okay, that's how you multiply polynomials. If I were multiplying something, let's do something truly awful before we go. How about x to the 4th plus 5x cubed plus 2 times x cubed plus 2x plus 1. Ooh, that's a nightmare. First off, this guy is degree 4 and this guy is degree 3. So their product's going to be degree 7. I know that for sure. That's going to come back and be very, very important in Unit 3. We'll call it when we come to it. Second, this is going to be like a box with 3 rows and 3 columns. So when I distribute everything, I'm going to have 9 terms for a minute. Now, hopefully some of those will be like terms, but 9 terms is a lot of terms. So I'll put x to the 4th, 5x cubed, and 2 in my rows. It doesn't matter which one's rows and which one's columns. Multiplication and addition are commutative, so it doesn't matter at all. I just did this by chance. Let's say x cubed, 2x, and 1 are the columns. One polynomial is the rows, one polynomial is the columns, but it doesn't matter which one's which. We're going to have 9 terms when we're done. You could pause the video and do this on your own just to make sure you get it right, but here I go. Multiplying by 1 is easy, at least. All right. Do I have any like terms here? I think the cubes are like terms, and the 4th powers are like terms, but I'm not seeing anybody else. So my final answer, x to the 7th, I'm just going to write this in standard form. I see a 5x to the 6th. Make sure you don't leave any boxes out, 2x to the 5th. Now for the fourth powers, there's a 10 and a 1. Together that's 11. For the third powers, there's a 2 and a 5. Together that's a 7. No squared, but a 4x and a 2. So that's my final answer. See, not so bad. Two trinomials. We could have as many as 9 terms, but some of those are like terms, so we ended up with only 7 in the end. A big polynomial. All right, so we've done addition and subtraction and multiplication. It turns out that dividing polynomials is its own monster. We don't need that tool yet, so we're not going to study it yet. We'll need it in Unit 3 at around the same time that we need these, so need the fact that this was a 7th degree, right? We'll need both of those facts at roughly the same time. What we're going to try to do is find out what values of x can I plug in to make the whole thing equal to 0. That's going to be what we do for most of Unit 3. And when we get to that question, we'll need to be able to divide one polynomial by another. But right now, that is unnecessary. So we'll study it later. This is enough for now. That's all I want to do about polynomials in Unit 1. We'll revisit them in Units 2 and 3 and learn a little more about them, but for now I'm happy. So that's all for now. Short section 1.4 is. Have a good one.